Hi, everyone. We just wanted to give enough time to people to have their connection work. I think we are all here and other people will be able to join us a little later. So I would like to welcome all of you. Thank you so much for being here with us today. I, of course, particularly would like to thank to Jenifer Wightman for being with us, and we are so excited to hear her presentation. My name is Işın Önol, and I am Thinking Food Futures co-curator along with Livia Alexander. On behalf of Residency Unlimited, we are pleased to welcome you to this two-day virtual symposium and exhibition, tackling one of the most urgent questions of our time. How will we feed ourselves given the intensifying challenges of food insecurity and climate change? We all know that the challenges on the table are complex, and bringing together artists and scientists, environmentalists and chefs, farmers and activists, we hope to generate different forms of speaking and engaging that go beyond isolated conversations in our small clusters of expertise. We invite you to join us over the next 2 days to as many of the events we have planned and to rethink together the future of food by radically reimagining the present. Jenifer Wightman embodies the ideas underlying the convening of Thinking Food Futures, weaving into her work, her training and professional practice, and critical thinking, as both as a scientist and an artist, exploring the co-evolution of life and landscape, and letting us speculate together. As a research scientist, Jenifer Wightman specializes in greenhouse gas inventories and life cycle analysis at Cornell University. She's currently working to establish an inventory, mitigation, and future scenarios for agriculture to meet New York State's goals of reducing greenhouse gas emissions 40% by 2030 and 85% by 2050. Her art practice employs scientific tropes to incite curiosity of biological phenomena and inform an ecological reflexivity. She has been commissioned by New York City's Parks, Science Gallery Bengaluru, and Cornell Biennial, featured at the Lincoln Center BAM and Imagine Science Festival, published in Orion Magazine, Pacific Standard, and Journal of Visual Culture, granted residency at MacDowell, Nordic Artists Center, and DJ Rassi. And her work, she has worked in collections such as Morgan Library, Library of Congress, Gutenberg Museum, Bodmer Museum, Russian State Library, and the Danish Royal Library. Thank you very much, Jenifer, for being with us, and we're looking forward to hearing your presentation. Jenny, are you with us?
I am. I'm just now sharing the screen. Do you see the screen?
Yep.
Okay. Do you see my desktop or do you see the PowerPoint presentation?
We were seeing your presentation well actually before.
You are seeing the presentation?
Yes, right now we are seeing it again.
Okay, great. It usually has a green line around it. So I had so much fun writing this title, and I just want you all to afterwards tell me how you interpreted the comma in which day of creation is it now? My abstract for today, sorry, I had more fun with that than I probably should have. I'm going to go quickly over some past depictions of our landscape, some of New York State's goals, some questing for future of landscapes, and then some hypothetical decisions our generations may make in response to climate change, and think about what kind of a scene do we set for future farmers on the landscape. And fundamentally, I am asking, if all there ever was is all there ever will be, what, if anything, do we do for those that come after? I just want to qualify that this talk is meant to be a playful joust, not a scientific talk. And I'm requesting how we can, as citizens, radically engage our local communities. That is the ultimate goal of this talk. So the first thing I'm going to share is a graph that changed my life. I saw this in 1999 in an environmental toxicology course I was in. And frankly, I wasn't someone who believed in climate change at the time. Or really cared about CO2 in the atmosphere, because I knew plants loved CO2. But this chart changed my life. And the reason is there's two trends. There's the obvious red line trend, right? Showing that from 1960 to now, we've gone from 310 parts per million to 390. Does everybody see the cursor?
Yes.
Okay. The other trend is an annual trend, and you'll see it going up and down. And that annual trend is pulled out in this little box here. And you'll see that we have higher emissions of CO2 in April or June, and lower total emissions in the Northern Hemisphere in July through October. And that's because you and me and everybody we know, including the microbes, are eating their canned peaches that they stored all winter and have been respiring them all winter. And so the CO2 is being released into the atmosphere. And then this falls back down over the growing months to have our lowest levels. Now this cycle repeats every year. And what was so shocking about the second trend, and why I changed my work from working on cancer cell biology to climate change, is because our life, our livingness of fossil fuel has emitted this much greenhouse gases. And all of the photosynthesis that happens on the surface of the earth is only this much for every year. This is what's going on. And that's tiny. I don't know how to express this, but if you don't get it, email me and I will talk to you ad nauseum about how important that is. On the whole surface of the earth, this is what happens every year, is this small little amount relative to the big amount of our fossil fuel extraction. So I've never actually presented this piece of art, but it's my first piece of art that I named Surge, and it's the ecological footprint of one Cornell student's paper consumption. And I'm using this to sort of situate this graph into sort of tangible understanding of the finite surface of the earth, right? Because all of this photosynthesis you see on this graph is happening on the finite surface of the earth. And so how do we think about that finite surface relative to our everyday lives? So I was writing my master's thesis. I was using a lot of paper, and a friend there was a big storm and a bunch of basswood trees were felled on his property. And basswood is a famous wood that's used for making paper. And I'd seen a book called Our Ecological Footprint. And it has equations on how you can convert resources into land areas. And I did that equation, and I made this installation. And on the left-hand side, you'll see what the average Cornell student uses in a year in a column of plexiglass. And on the right-hand side, you'll see 500 square meters of tree stumps. And I was trying to help visualize how much area of the world I needed in order for me to pursue my academic aspirations. So that's 500, just put it in your head that where those tree stumps are is about 500 square meters. And that column of paper is how much area you need in order to supply that annual consumption of paper. For context, my Bronx apartment, which is 700 square meters or square feet, is, and if I divide it by the 7 floors that I share it with, so I'm sort of cheating here, but I'm trying to make a point about densification in cities. My apartment is 10 square meters. My point, every object I purchase comes from some leased area of the earth. So somewhere in this world, there's 500 square meters that is my personal paper factory. So here is a picture of New York State forests. So maybe somewhere in there is my paper factory. So I'm gonna segue, I'm gonna jump around a lot. from some great art from the New World, specifically focusing on the Hudson River School of Art from the mid-1800s, American landscape painters, sort of born out of the Hudson River, but they went beyond, and some famous names are Thomas Cole, Friedrich Church, Albert Bierstadt, Asher Derland, and George Inness. And I'm going to ask you to think about words that come to mind so that when we think towards the future, we think about the words we want to have for future generations. So for me, this is majestic. For me, this is scary or adventuresome. To me, those red coats in the foreground makes me understand why people were so wanting to fight over this land, because the proportion of land area per body is quite large. Prospecting. On the right-hand side, you start seeing the civilizing power of agriculture. And on the left-hand side, you still see the tempestuous storms, so sort of this in between. This painting has a sense of scale that is very approachable. I'm not daunted. I want to go adventure into it. This is comforting. And I'm going to end with this George Inness painting of the Lackawanna Valley in 1856. You can see, of course, the train system has been developed, and in the foreground, you can see all of the tree stumps that have been cut to build all of those homes. So I'm thinking of these paintings as something of a documentary of ways in which our country looked 200 years ago. And to think about what it is we want to go forward. So the Hudson River School to me reflects on three themes of America in the 19th century: discovery, exploration, and settlement. From diabolical fear of nature, heavenly admiration of nature, coexistence with nature, utility of nature, and mastery of nature. So in New York State, in the beginning, it was mostly forested, but by the 1880s, agricultural land had peaked with 80% of the area as farmland. We cut our forests to build our homes, to heat our homes, to grow our food, and grow food for our horse transportation systems. Today, we're 60% forested. Is that because we like forests more than ag, or because we like forest songbirds better than field songbirds, or because New York State has great forest policies? Or is it because we discovered fossil fuels? Because in 1825, the first natural gas was found in Fredonia, New York. By the late 1870s, the first major oil field near Orland, New York. So if you look at this graph, right, you can see that wood peaked at around the 1870s or 80s, just when all of these fossil fuels started showing up. So we were living on this amount of energy in the 1880s compared to adding all of these things on the right-hand side, right? So they're shown as individuals, but we need to add them together to see the comparative amount of energy that we're using today. Now let's think about when those paintings were done. I love the scale of this graph because it's got 1 million years ago, like all of these tiny amounts of humans. And these paintings were done between the 1800s and the 1900s, so there were 1 billion people. My parents were born in the 1930s when there were 2 billion people. I was born in 1973 when there were 4 billion people. And now my parents have to share the cookie with 8 billion people when they only used to have to share the cookie with 2 billion people. So I just want to again stress that those paintings were done when we had this many people on the planet. It's the same landscape. So then I have to ask, if all there ever was is all there ever will be. So I'm going to give you 4 examples. Friedrich Church, one of those painters, he's one of my favorite artists because he really was a conceptual artist, because at some point, instead of painting, he actually started landscaping. And so this used to be a bog, and he had people dredge it in order to apply it to agricultural land to improve food production, in order to make a beautiful lake outside of his picture window. Another way of thinking about it is 500 million years ago, there were 2,000 to 8,000 parts per million CO2 in the atmosphere. When I showed you the graph at the very beginning of the Keeling curve, it was only 400 parts per million. There was this huge burst of life, trilobites, fish, coral, snails, tetrapods, ferns, so much life and so much carbon sequestration that became our fossil fuel. So you're struggling with a COVID shutdown, think about all that poor carbon trapped in fossil fuel, just begging to get back to the surface. So here's a graph. These are models, so this is theory, showing back 500 million years ago, between 2,000 and 7,000 parts per million, all getting sequestered into biomass, which became our fossil fuels, which we have the opportunity to release back out to the atmosphere. Example 3, creation 2.0, just do it yourself. This paper that just came out this last month indicates that we now make more human-made mass than animals, and more building and infrastructure than trees and shrubs. So humans are making more stuff than all the living animals and trees and shrubs. Example 4, why have mountains? Why not fill in the valleys? This is a topographic or a picture from Google Maps. On the right-hand side, you'll see a mountain that over my childhood has been reduced to almost completely flat. This is the road I would take in order to go to Kmart to get all of those objects that we're talking about. And what's interesting to me about this image is not only has the mountain on the right become flat, but the valley on the left has become a landfill. And so the valley has been filled in with all of the stuff that's being taken out on the right. And I'm just trying to point out that all there ever was is all there ever will be. We've just moved it around, right? So I'm starting to enter the speculative part of the talk. And this is a 1990 science fiction story called Earth. And this is a little section in it. It might have been predictable, and yet few saw the answer coming. In a later day of harder times, of short resources and mandatory recycling, it was inevitable that these landfills should draw the eyes of investors looking for ways to get rich. The same finite materials, just differently located. So, New York State context. How much is New York State emitting? Well, in our most recent report, it's 206 million metric tons of CO2 equivalents. And of that, agriculture is about 4%. Most of this is coming from fossil fuel consumption. So 173 million metric tons of CO2 is coming from fossil fuels. That's 84% of fossils yearning to be free. I mean, they just want to come up to the surface and cycle with us, wouldn't you? So we don't really want that to happen. And under the Climate Leadership and Community Protection Act, the CLCPA, which was signed by our New York State legislature in 2019, and you can check out more at this URL, we have set goals in New York State for 40% reduction in greenhouse gases by 2030 and an 85% reduction by 2050. We have all these different initiatives, including 70% renewable energy by 2030, 9,000 megawatts of offshore wind, 3,000 megawatts of energy storage, 6,000 megawatts of solar, 22 million tons of carbon reduction through energy efficiency and electrification. So, what do we have as area to work with? In New York State, we were 80% ag land, and now we're 62% forest and about 25% ag land. So if we broke that up on a per capita basis, like if we said you, me, and everybody else got the same amount of area, that means we each get 6,273 square meters for a New Yorker. And New Yorker, I mean New York City and New York State. That means 1,400 square meters of ag land, 3,800 square meters of forest land, and 972 square meters of other. So what do we do with it? How do we consider this area for the next generation? If you had control of this amount of area, what would you do? Did past generations anticipate that what was on the left would turn out to be what was on the right? And was that a good decision? I would argue that the density of New York City is one of the best things that's happened in New York State. But did those that came before plan for us? And could they have? So this is where I'm shifting to what shall we do? What should we do with this area? And how shall we think about the next generation of people who lead on this landscape? Do we reduce food imports? This is a paper from 2019 showing food flows. Where is all the food coming from and where is it going? This is from a New York Times article in 1981. By 1981, we were importing 85% of our food. At that time, we produced all of our own dairy. We were only producing 4% of our carrots. Like, have you thought about where the 96% of your carrots come from? Or the 86% of your celery? Or the 85% of your cucumbers? Because we did produce 17% of our own radishes. This is New York State, where our agricultural and hayland is located. So, do we grow as much food as possible? Do we become vegetarian or go paleo? Do we mandate 100 cow farms instead of 1,000? Do we have dairies become high-tech systems? Do we move to sheep or goats that graze across the landscape? Do we harvest deer as food and improve forest health from deer browsing? Do we invest in compost-heated greenhouses so we can have tomatoes in the winter? Do we return to canning our seasonal food again? Do we invest in soil robots to maximize food grown per acre? What do we New Yorkers do with short-term growing season and long cold winters? Or do we just keep importing from the Midwest and California? There is serious work on 2-foot-long worms, just so you know, to analyze robots within the soil. That's just, I had to put it in there. Do we change the diet? And whose diet? Do we change the diet and microbiome of cows? Do we deploy microbial scavengers to reduce their enteric methane, which is their gut methane? Do we change our own diet? Or do we change our behavior of food waste? If 31% of our food is wasted, as the EPA has estimated, if we cut that in half, what could we do with that ag land that we're no longer wasting on food, right? Because for every percentage of food that is not wasted is a percentage of acres that can be used to do other things. Do we do carbon storage? So do we grow as many trees as possible? Like, we forget the agricultural land, we just put trees right back on there and sequester all the carbon in the trees. Do we leave those trees there? Do we cut them down? Do we burn them and use the energy to compress the combusted CO2 back down into our oil wells? Do we turn it into biochar and apply it to our ag land? Do we turn it into furniture and houses that live for another 100 years, holding that carbon for another 100 years? Or do we chain them together and bury them at the bottom of anaerobic lakes where they don't decompose? So bioenergy, carbon capture and storage is the idea that you take all of these trees, you put it in a woody biomass plant, you get a certain amount of energy out for society, but with some more energy, you compress that into liquid form and you put it into old reservoirs, oil reservoirs. I just want to caution us that compressed CO2 is what is organic dry cleaning, and it is a very good solvent. So putting a solvent down into our reservoirs is maybe not the best idea. Anyways, it's one idea. And of course, we need to do full life cycle analyses on this. Do we do basically the same thing, only we do incomplete combustion so that we've got this charred form of biomass? And because it's charred, it doesn't decompose easily, so it lasts another 100 years in our soils. It's called biochar. Or do we do Jurassic bark? I'm not kidding. This is a guy in Wisconsin who found all of the lost logs that were harvested back in the 1800s that sunk as they used rivers to transport logs, and pulling them up. And in Japan, there is this concept of burying logs, large diameter logs, so that future generations have large diameter pieces of wood. Because deep at the bottom of lakes that don't decompose. So we could sequester huge whole trees at the bottom of our water systems. Do we displace fossil fuels with biogenic carbon? Do we maximize our biomass and burn it to displace as much fossil fuel as we can? Do we grow short rotation willow or switchgrass or reed canary grass? Do we grow poplar trees? Do we grow regular forests and harvest them quickly? This idea is that the carbon is sequestered into the tree and then we burn it and it's released to the atmosphere, so there's no net gain. And that's in contrast to pulling up these fossil fuels from deep in the earth from 300 million years ago and resulting in a net increase of CO2 in the atmosphere. So is the landscape going to look like these grasses for that bioenergy displacement of fossil fuels? Will it look like the short rotation woody crop that gets cut every 3 years? Do we want to maximize fossil fuel displacement so we keep those fossils in the ground? And what's important here is that fossil fuel carbon dioxide, 30% of it is still remaining in the atmosphere after 100 years. 15% of it is remaining for the next 1,000 years. So everything we do to keep fossils in the ground helps keep this carbon from cycling and changing our climate. Do we displace fossil fuels with wind and solar? Here's a wind map of New York State. Here's a comparison of New York State solar potential compared to Germany. And I don't know if any of you have been to Germany, but almost every house in Germany, it seems, at least when you're riding the train, is covered with solar panels. And you can see by comparison that New York State has a far more favorable solar potential for producing solar than in Germany. What I love about this picture is that the solar panel array here looks very similar to the water systems over here. Do we forego biologic sequestration of carbon and just do solar displacement of fossil fuel? Do these solar panels go on prime agricultural land? If they go on prime agricultural land, does a developer have to pay a fee to support buying and conserving other ag land? Where and what quality? There are rumors that farmers can make $1,000 an acre if they put on solar panels. There isn't a crop that can compare to that. Should we reconsider what we pay for food? Should we reconsider what we pay for energy? At the end of the day, we can't eat electrons. And yet, 80% of our emissions are coming from fossil fuels used for energy. Do we do agrivoltaics, where we grow food or animals in between solar panels? If an average New Yorker uses 572 kilowatt hours per month, I have made a very crappy, very quick, as of today, calculation that we need 22 square meters a person, right, of land area for this average amount of kilowatt hours per month. Do we design replicators so we don't need to grow food on the land? We use electrons and waste materials to grow food on spaceships in outer space. I'm being totally cheeky here. Do we densify the human population? If we all lived in cities, maybe we wouldn't need 240,000 miles of roads. I've estimated that's roughly 875,000 acres of roadway. What if we just eliminated the north-south highways as corridors for animals to move, and they can carry the seeds with them to their preferred climate? So in other words, as they carry the seeds from the fruits and things that they eat, they drop them and they naturally acclimate in new climates. So we have a way for our agriculture and trees to move north and south according to changing climate. Here's an Akron art intervention. They decided to reclaim a highway, and in order to do so, they had a dinner party along the highway in order to decide what they would do with this area. So in sort of a peculiar summary, I just want to sum up some partial land lease ideas. If my paper, my sustainable paper requires 500 square meters and my apartment divided by 7 floors that share the same square meters is 10, and the New York food land is 1,435 square meters, and we import 85% of our food, how many square meters is that? And if we consider our share of our New York State highways of 89 square meters and a solar array just for my monthly solar needs of 22 square meters, I haven't even added in my home heat or my transportation fuel. I didn't have time. What do we want to do with the land that we have? And I'm just making another sort of joke on get back to the land. And in this case, I would say join your city and regional planning board. In part because in the United States in the 1840s, there were 17 million people. That is roughly equivalent to how many people there are in New York State today. So if you're upset about federal policies, focus on New York State because we are huge as a state. If you're thinking about perspective compared to other places, the US, the average person is emitting 15 tons of CO2e equivalents per person per year, compared to Colombia of 1.5 tons of CO2e per person per year. So I, as a US citizen, emit 10 times more than one person in Colombia. If we compare the United States to New York, I, as an average New Yorker, emits roughly 1/2 of the US citizen. And in part, I would argue that's because we have such dense population in New York City, which is conserving energy. However, these numbers do not incorporate all of our imported foodstuffs. So you have to be a little skeptical about that. Now, if we compare New York State to Denmark, and Denmark is the poster child for climate mitigation. They're very progressive. As a New Yorker, I emit 50% more than one Danish person. But as a New Yorker, legislatively, if we can change policies in New York, we can change the policies for 3 times more people. So let's think of ourselves as a state that can have real power in the global scheme of things. So I no longer care about the Anthropocene. We're totally here. Like, what are we going to do about it? By living, we change things. So let's change things. So what do we really want? Really and truly, what is important? So do you agree that in a balanced world, all there ever was is all there ever will be? And if so, what do we want to see with the what is? What do you want to shape for those that come after? This is a picture of me with my 2015 Sustainable Systems students. This was the year that the world proceeded with the Paris Climate Accords. So in this great chain of causes and effects, no single fact can be considered in isolation. Alexander von Humboldt was very inspirational to those Hudson River School painters. And I think we can return to some of his thinking today and think about how we are part of the chains of causes and effects so that we can think about the landscape for the next generation. And here's a pie chart I made in 2009, and it's split up. Transportation is this big section on the right-hand side. buildings, and this is electricity. So if you want to think about New York State energy consumption, think about how you can make your impact to transportation, buildings, and electricity use.